Going to finish off our study of applications of singularity analysis by looking at another schema that generalizes the simple variety of trees and covers again a whole host of a whole family of combinatorial classes called tree-like classes. So for implicit varieties of trees, we said if you get the generating function of the form f of z equals z times phi of f of z, a root and some stuff, that's a tree, that's a simple variety of trees, then we can go ahead and analyze it. So for implicit tree-like, we say, well, if you have any function of z and f of z, it doesn't have to just be z times f of z, then that's what we're going to call an implicit tree-like class with characteristic function phi. In the unlabeled case, number of structures is z to the n f of z. So we can have any constructs that are plus Cartesian product and sequence. In the labeled case, your number of structures is n factorial z to the n f of z. Again, you can have any set of constructs where it's an arbitrary composition of our basic operation sequence, set, and cycle. All of those things are going to come down to a generating function equation of this form immediately by symbolic transfer. And we'll look at some examples of this in just a minute. And as I pointed out, this generalizes simple varieties of trees, where if we just take our general function capital phi to be z times little phi of w, that gives simple varieties of trees. Here we're allowing arbitrary functions of z and f of z, implicit tree-like classes. Now we have this smooth implicit function condition. Again, for all of our schema, we have some technical condition that we have to make sure is satisfied in order to be able to push singularity analysis all the way through. Usually the technical condition involves eliminating trivial cases, but there's also periodicity and problems with singularities the same distance from the origin that also are involved in these. And so here's what it is for implicit tree-like classes. So we've got our tree-like class f equals the construct of f, that's generating function phi z of f of z. So we say it's smooth implicit if its characteristic function satisfies conditions, and here's the conditions. So it's got to be analytic in a domain with its two values less than some values r and s. So that's and these functions are usually very simple functions, so that's not a problem. It's got to be non-negative, and it's got to actually not be zero for some values. So that's again removing degenerate conditions. I won't spend time on that. And there's a characteristic system, not just a characteristic equation. It's got two values. And so if you take phi of r of s equals s, and the derivative with respect to w phi of r of s equals 1, and you solve that characteristic system and you get good solutions that are reals, positive reals, then that's what smooth implicit function is. That's the main condition. This characteristic system has to have a solution in reals in the domain of analyticity of the function. And again, these functions, as we'll see, are usually pretty simple. So here's an example of a tree-like class, and we'll look at this later on. This is phylogenetic trees, it's called. So L is Z plus a set of at least two L's. That's the Z, a set of at least two. We take E to the L of Z and then subtract off 1 and subtract off L of Z. So that's not a simple variety of trees. It's not z times something. It's this complicated function. But that's fine. It is a implicit tree-like class because the characteristic function is z minus 1 plus e to the w minus w. And then we can write down the characteristic system, which is set that equal to w and set derivative with respect to w equal to 1. So z minus 1 plus z w minus w equals w. The derivative of this with respect to w is just e to the w minus 1. Those go away. E to the w minus 1 equals 1. That's easy to solve. That means e to the w equals 2, or w equals log 2 is the solution, so s equals log 2, and then we plug log 2 into the other one, and we get r equals 2 log 2 minus 1. So we found the characteristic system. It's got a solution that's real. And so that means that phylogenetic trees are smooth implicit with those parameters R and S. It all depends on this characteristic function and the characteristic system. And again, if we can establish this, which often we can with simple calculations like this, then all the work of singularity analysis, of finding the delta domain and approximating the functions and so forth, is all under the covers, and we can immediately get the asymptotics. So this is the theorem for asymptotics of implicit tree-like classes. So you have an implicit tree-like class. It's aperiodic. Again, you can't have any regular recurrence of coefficients in there, and that's discussed in the book, and we'll ignore in lecture. So it's smooth implicit with parameters R and S, so that phi of R and S equals S and phi sub W of R and S equals 1. Then it's going to, then R is a place where it's got a square root singularity, and we can approximate the generating function at that singularity by S minus alpha square root of 1 minus Z over R, and that approximation gives us the coefficient asymptotics, which is 1 over R to the n minus 3 halves times a constant, and that's how to compute the constant. Very similar to, for simple varieties of trees, it's just a more complicated computation of a constant, but not all that more complicated. And again, we've got coefficient asymptotics now of a 1 over R to the n into the minus 3 halves times a constant for any construction, any kind of recursive construction, where we've got a class defined in terms of itself and atoms. Like for example, binary trees. If we use the other construction of binary trees, where it's a node or a root and a sequence of 0 or 2 binary trees, another way to define binary trees. Now our equation is z plus zb of z squared, so that gives the characteristic function z plus w squared. There's the system. Then s equals a half, r equals a quarter. Then we can compute the derivatives in alpha and immediately get out the coefficient asymptotics just as before. So that's a transfer theorem for implicit tree-like classes, and binary trees is a simple example. So let's look at a more complicated example. A famous complicated example leads to what's called Schroeder numbers. A German mathematician called Schroeder in the 19th century studies a lot of problems like this. And this is one. So a bracketing of n items is a tree that's got n leaves, so the black ones are the leaves here, and no unary nodes. So and there's lots of applications of this that are described in the book on page 69. So how many bracketings with n leaves? So here's all the bracketings, say with 3 leaves. You can have a root and 3, or you can have 2 on the left or 2 on the right. Again, no unary nodes. All nodes are either degree 0 or they're degree 2 or more. And the size is the number of leaves. So there's 11 of size 4 and so forth. That's equivalent to the number of ways to parenthesize n items. In part 1 of the course, we talked about correspondences between trees and parenthesis systems. And if you go back and forth between these slides, you can see the correspondence between bracketings and ways of parenthesizing n items. So here all 4 are in the same parenthesis system. Down here we have 3 with 1 on the right or 1 on the left and then 3 and so forth. So that's what Schroeder was actually interested in, was parenthesizations. And there's many other ways to look at this. And or conjunctive propositions, or trees where and ors alternate, or what's called series parallel networks. All of these things are equivalent to bracketings. So they are found in all sorts of different applications in combinatorics. So what does it look like from the standpoint of analytic combinatorics? Well, a bracketing is a node or a sequence of more than 1 bracketings. It's interesting to note that combinatorial specification is probably the most succinct way to describe what a bracketing is. And that's often true in analytic combinatorics. We're talking about succinct ways of specifying things, and it turns out that those lead us directly to automatic ways to enumerate them. But that certainly is an important part of the science, is what is it that you're trying to count? You need to specify it, you want to do it succinctly, and combinatorial constructions are not a bad mechanism for that. So as usual, that translates immediately to the generating function equation. So we have to subtract off the size 0 and the size 1. And we could go ahead and solve for that and so forth, but the implicit tree-like classes says you don't really have to go ahead and solve for that. What you have is your function is expressed as a function of z and itself. That's all you need to see. And then as soon as you see that, then you can get the coefficient asymptotics. I'm not going to do the details for this example. That's left for your exercise for this week. I'll do a more complicated one. This is slightly more complicated. It's not that much more complicated. It's a labeled version of the same problem. So that you have a lot of labeled leaves, and you're trying to collect them together and provide a hierarchy in some way. And this turns up in lots of scientific and commercial applications related to evolution and many other things. And it's another problem Schroeder studied in the 19th century. So many applications of this sort of thing. So this is the number of different labeled hierarchies of n nodes. Where now there's not only different shapes, but there's different labels. So you can put 1, 2, 4 together and 3 apart, and that leads to that kind of thing. And the order of in the tree doesn't matter, but the way in which things are grouped matters. So I won't go through the details, but that's anyway the number of labeled hierarchies. And again, the spec is the most succinct way to define it. Labeled hierarchy is a node and a set of at least 2 labeled hierarchies, that's all. So the generating function equation, again, it's z plus all the labeled hierarchies, that's e to the L of z, subtract off the 0, subtract off the 1, as we've done many times before. But now from the standpoint of this tree-like schema, that's as far as we need to go. It's just a function of z and itself. So that means we can apply the theorem for implicit tree-like classes. It's a function of z in itself. Just have to identify what the function is. In this case, it's z plus e to the w minus 1 minus w. You make a system of equations by setting that equal to w and its derivative equal to 1. That's the system of equations. Derivative with respect to w, z to w minus 1 equal 1. E to the w minus 1 equals 1 means w equals log 2, and then plug w equals log 2 into this one, and you get r equals 2 log 2 minus 1. So now we compute the other derivatives, a derivative with respect to z of the characteristic equation evaluated R and S, and a second derivative with respect to w. So those are the calculations. Derivative with respect to z is just 1. First derivative is in respect to w is EW minus 1. Second derivative is e to the w. Plug in those values of r and s. And actually, well, it's 1, the derivative is z. Second, with respect to w at r and s is log 2, it's just 2. So that means alpha equals just the square root of r, which is 2 log 2, square root of 2 log 2 minus 1. So those simple calculations, boom, give us the complete coefficient asymptotics for this class of labeled hierarchies. It's an implicit tree-like class, and we have top-level analytic combinatorics getting us right to the coefficient asymptotics. Again, all of these methods, there's ways to find it with specific techniques oriented towards each problem. The beauty of singularity analysis is that all that calculation is hidden under the cover and done once for us, and it's organized then in terms of a few broadly applicable schemas. And if you want to have hierarchies, if your scientific problem you observe in the field that's really better modeled by a set of more than 4 things, or sets of 3 and 9 things, or whatever it happens to be, you can write down a construction, you can test that construction against what you're observing in nature, and then you can get the coefficient asymptotics immediately via applying a schema of this type. It's a very broad and general way to get to the useful information that's needed for whatever scientific endeavors involved. That's a fourth example of a schema based on singularity analysis, tree-like classes.